Just turn the master volume up.
Almost there. I can hear myself. Perfect. All right, hello, and welcome back to Space Drafts. This is Space Drafts 99. Thank you for sticking with us through our summer hiatus. Now, for those of you who don't know, Space Drafts is a part of an international network of astronomy on tap events. We share astronomy with the public in bars and pubs around the world, and it is a great pleasure to do so. My name is Nick Schragle. I am a graduate student at the University of Arizona in the Department of Astronomy. For those of you here for the first time, welcome. This is a show where we have two wonderful astronomers come and give you 20 to 30 minute talks. Between each of those talks, we'll take a little bit of an intermission, and we'll have recent updates from astronomy in the news. Now, during our two talks, we will have some trivia questions for you to answer. If you are the person who answers those trivia questions correctly, you can come over to our merch table over here and get a prize. And speaking of merch table, we have merch. We can only accept cash from you, but we have merchandise, we have posters, we have buttons, I think we have magnets, we have some glasses to help support us. All the money all the money that goes into merch comes back in us buying more merch. So thank you for purchasing. One last thing before we kick things off, we are stationed here at Borderlands right next to an active train line. So it is a custom here at Space Drafts that every time a train comes by and interrupts our speaker, we raise our glasses and toast it with a hearty choo-choo! Now let's get things started. We have a great show for you tonight, and we are going to be taking you back to the earliest epochs of the universe. Our first speaker is bringing us to one of the earliest known galaxies in the universe. Please give a warm welcome to Associate Research Professor at the University of Arizona, Dr. Kevin Hainline.
There's a clicker here. Great. Let's click over. Hi, everybody. Are you having a good night? Yes? Well, great. I appreciate you all coming out for science. This is pretty rad. And if you're on the patio and you don't like science, tough. I'm Dr. Kevin Hainline. I'm a researcher at the University of Arizona here, and I'm going to talk to you about something that I'm very, very excited about, as you're about to find out. If you enjoyed this talk, this is kind of a short version. I'm giving the Steward public lecture next week on Monday, and it'll be a little bit longer, more robust version of this. There'll be some repeats, but this is the kind of fun, we're all having a beer version, if that's okay. And also, I like to put some social media stuff if you want to find me and email me, ask me questions or whatever, or follow me on TikTok. Yeah, that's right, I'm 41 as of yesterday, and I have a TikTok account. But we're going to talk about the earliest galaxies, and we're going to talk specifically about something called Jade's GSZ 14-0, which you're going to hear me say 1,000 times, and I apologize. So let's talk about the universe, the history of the universe. And the history of the universe is something where the universe is about 13.7, 13.8 billion years old. If you put that on a timeline like this, today's over here on the right, and the early Big Bang is over here on the left. If I zoom in on just the first 1.5 billion years, that's what we put right here. We put the Big Bang over here on the left, and between the Big Bang and the first stars, that's the next talk. Stick around, the next talk is actually not even that, but just right here at the very pixels right there is the next talk, which is very exciting. But I'm going to talk to you about most everything that happened from here down. And we're going to talk about the way the universe changed from the Big Bang to, when the universe essentially had galaxies, and then there's many billions of years of galaxies. And the thing is when we look at charts like this, you might say, well, how do we know this? How did we know about when the first stars happened, and the first galaxies, and the first black holes? What do you mean when you say the universe is transparent? How do we know all that? How do we know? How can we make charts like this one, which is from National Geographic? How can we make charts like this? How do we know this? And the answer is, we take pictures of it. So, back when I was much younger, NASA put into space, on a space shuttle, a thing called the Hubble Space Telescope. And the Hubble Space Telescope, which was put into space in 1990, took incredible images of the universe, but then it did something that completely changed my life. It took a set of images that you're seeing here. These images, which are in some cases older than some of the graduate students who are sitting here, which really turned 41 yesterday. Anyway, this image here was fundamentally important because it was in books. I saw it on Nova. I watched a lot of Nova as a child. And has anybody ever seen this picture here that's labeled on the bottom? Seen it before? If you haven't, this picture has an incredible story, which was that scientists, when Hubble was up there, started noticing when they essentially fixed the astigmatism of the telescope, noticing that in the backgrounds of a lot of the pictures from some of their cameras were lots of galaxies. And so they went to the astronomy community and said, astronomers were like, should there be this many galaxies? And some people were like, no. There's a very famous astronomer named John Bacall who once wrote, Hubble will never discover a new galaxy. He'll just give us nice pictures of the ones we already know. True story. Sorry, John, because the director of Hubble at the time took aside a big chunk of time that he had to do whatever he wanted to and pointed it at a region of the sky, spurred on by a group of astronomers that said, based on what we're seeing, I think if we open the shutter and really, really stare over like Christmas of 1994, 1991, we'll get something like this. And this picture, which represents, maybe like 100 hours of JW's Hubble time, came back and there was thousands of galaxies. Galaxies that had never been seen before. Galaxies that completely changed astronomy at the time because many of these had never been seen, and the only time and the only way we could see them is with this. And this image, and then when they looked at a different region of the sky deeper with the Hubble Ultra Deep Field, that's why astronomers are very good at naming things. We just append ultra, mega to the name, and that means deeper. When we looked at this, we saw that in multiple regions of the sky, the universe is just filled with galaxies. Galaxies. Every smudge on here is a galaxy, meaning billions of stars, hundreds of billions of stars in a big gravitational field. And these two images caused an incredible stir and a revolution in the way that we looked at the universe. Because when we look at galaxies that are very far away, we're not seeing them as they are right now. It takes time for that light to travel across the universe to our eyes. So the farthest galaxies we're seeing in this image, we're not just seeing them billions of years ago, we're seeing them many billions of years ago. And in fact, the farthest galaxy that had ever been seen by Hubble is this object called GNZ11. And it's a galaxy that is, from just a couple, like 400, 500 million years after the Big Bang. An infant galaxy in an infant universe. This was discovered, in 2014, I think, in 2014 by an astronomer named Pascal Oesch. And it really caused quite a stir. It's a big deal galaxy. It's called GNZ11 because it's in a region of the sky known as Goods North. Goods North is essentially around here. They did a bigger tile and GNZ11 somewhere up here. This is Goods South, which is the southern version of it. And this galaxy, so many people went after to try to understand. It was called GNZ11 because they thought it was at a redshift of 11. Redshift is a number we ascribe to astronomy objects, distant galaxies, and 11 was, unimaginably high. The farthest galaxy seen in like the 1970s was a redshift of 3. It was so far away that astronomers, the Time magazine wrote a whole article about it and called it the blaze at the edge of the universe. And 40 years later, we go redshift 11, right? But this was where Hubble kind of left off. And then we built this and launched into space. The last time I came and stood here and spoke to Space Drafts, this had just launched, and it hadn't even taken any science data yet. And I'm really excited to be here again to tell you about some of the cool science data it's taken, because while Hubble was amazing, it was limited. The reason that this was the farthest galaxy was not because Hubble couldn't see it, or Hubble wasn't big enough of a mirror, but because Hubble was not an infrared telescope. It had some capabilities of seeing infrared light, but it kind of capped off about what we call 1.6 microns, which JWST goes all the way out to 30 microns in one of the instruments, and in the instrument that I work on, that we're going to talk a lot about, NIRCam, it goes to 5 microns, which means that it was limited by not being able to see galaxies farther than this, because all of their light would have been shifted to longer wavelengths, and Hubble couldn't see it. It could stare forever and never see galaxies significantly farther than this. So this telescope, which way, way, way bigger, Hubble's mirror is, probably like this big. This is like 21, 22 feet across, really big. People probably talked for hours about JWST. The telescope is a real miracle, and it's done an amazing job of looking at the distant universe. This is a field called JADES. There's many fields that JWST has looked at that are ultra deep fields of the universe, but one of, and I'm very biased because I work on this, one of the crown jewels of the first couple years of JWST has been this field here. which has essentially opened up the universe in a way that Hubble never could. It's deeper, it's bigger, and it's at a wavelength range that Hubble couldn't see. And so when I show you Jade's good south here, actually this is just a zoom in, it's much bigger. And this is early public data. We have data that extends out here. There are people sitting in this room, or on this patio, who you don't even realize secretly are experts in parts of this, at wavelength ranges of this. I have looked at hundreds of thousands of galaxies. There's so many little smudges here. This is the good south, and Jade's, the JWST Advanced Deep Extragalactic Survey, has a northern counterpart. But first, I forgot, this is the Hubble Ultra Deep Field. This is where it sits. I showed you that. This is how much bigger Jade's is compared with the deepest that Hubble had ever seen. And again, all of this is significantly deeper than this Hubble Ultra Deep Field. And there's a northern version. This is the Goods North version, which I just talked to you about. And here's the Hubble Deep Field. The very famous Hubble Deep Field is just kind of nestled in one little corner of this very big region. And we have more data around here, and there's ever more data being added to this as scientists get their proposals accepted. So here's our question before we get to the last part of the talk. Galaxy redshifts, I just talked about redshifts, were discovered about 100 years ago. And who was the first astronomer to look with a telescope spectrograph and see that galaxies, spiral nebulae at the time, were actually galaxies and receded, had redshifts? Who discovered the concept of redshift? Henrietta Swan Leavitt, Edwin Hubble, Willem de Sitter, Vesto Slipher, or Georges Lemaitre? All right, so I want to see this right here. Yes. Hubble is incorrect. Seems like it should be, right? Not Hubble. Pretty good guess, though. All right, right there. Yeah. Who'd you say? Henrietta Swan Leavitt. Also incorrect. This is a fun one. Every one of these people played a part in this, but there's one person that you probably are like, I didn't even hear that guy. Yes, right here. Vesto Slipher is, in fact, the correct answer. In Arizona, up at Lowell Observatory in 1912, first looked at galaxies and discovered they were receding. Henrietta Leavitt did the work to make sure that Hubble could understand the distances of distant galaxies, but it was Vesto Slipher, who, if you've never looked it up, look him up. He's an incredible astronomer, did work for decades up at Lowell Observatory, and found the first redshift. So whoever is, giving away prizes, congratulations. So, when the JADES data first came out, there was a mad scramble. Our team, the JADES team, had essentially set out and thought, well, what's going to happen is that JWST will observe the JADES field and get data to us, and then we'll have 40 days, based on the schedule, with which we can look through all of these new galaxies and find very far away galaxies based on their images alone. And then the schedule kind of slipped, and eventually it was discovered that actually that 40 days is going to be a year because of the way it's going to work. We couldn't go back and look at the things and get spectra and confirm for a year. So we were like, well, I guess we'll have a long time to really make sure we do well. Then the schedule slipped one more time, and they said, hey, I got an email, and all the JADES team got an email from one of our heads, this guy named Daniel Eisenstein at Harvard, saying, if you can get candidates for us in 5 hours, we can maybe confirm them. And it led to an incredible mad scramble. Some of you here maybe have seen someone who's worked tirelessly as part of the Space Drafts effort named Lily Whitler. She was independent to me, scrambling through thousands of galaxies. And we identified 9 objects in 5 hours, most of which had never been seen before. We took those 9 objects and we looked at where we could get spectroscopic follow-up with JWST 1 week later. It took a while for us to get this, that's why we had 5 hours. We needed to go through a whole bunch of rigmarole to make sure we could even do this. And we found 4 objects we could put onto NearSpec, the JWST instrument, to confirm the distances. And so this is me saying, all right, here's my 4 predictions, kind of like Babe Ruth walking up to bat, pointing to 4 spots in the outfield, and then taking 4 pitches. Every one of these 4 galaxies came out at the redshift we predicted it, including this one right here. JADES GSE 13.0, which is at a redshift of 13.2. This was the farthest galaxy, the JWST, that humanity had ever seen. Discovered here at the University of Arizona on a computer that I do not use anymore because it is too old. It's very exciting, and it looks like a little red smudge. This is from when the universe is only like 320 million years old. Baby universe, tiny little red smudge. This is what most distant galaxies look like. they looked like little red smudges. Some of these had been seen by Hubble, and we were seeing them again with JWST, but this one, you can look super deep in all the Hubble images, it doesn't appear. Too far away, Hubble could not have seen it. And I looked at a lot of these objects. Oh, I should say, this is a Guinness World Record for most distant confirmed galaxy, which is kind of fun. I like this because it says that it was discovered by the James Webb Space Telescope, as if it's discovering galaxies on its own. Do you guys not see the University of Arizona anywhere here? Yeah, come on, Guinness. Also, it says where, not applicable. I can tell you exactly where on the sky. Good, it's fine. I wrote a paper last year that had where I did a very careful search, where I didn't just have 5 hours. I used a lot of help. Some of the people here helped me with this, where I looked through a lot of galaxies and identified over 700 galaxies that were some of the farthest that humans had ever seen. But they were candidates. I found them. I said this could be really far away based on all the predictions and estimates, but we need spectroscopy to follow them up. But you can see every dot here is some potential very distant galaxy. And this right here is, I think, one of the great discoveries of JWST, is that this is not just these fields. There are so many fields. There are people, again, here who do this with other fields and other data. Look for distant candidates, understand their distances. And it's something that when we were worried about, okay, will JWST launch correctly, will it get up there? I was also worried because we could have looked for very distant galaxies farther than what Hubble could see and saw nothing. We could have just seen nothing. Maybe the universe didn't make galaxies until way late. But what this is showing us is the universe is very giving with its galaxies. And galaxies came on the scene much earlier than we thought and were very, very bright early on. And there's a lot of them. It's really, really exciting. So in February of last year, I was looking through some of my candidates, and I saw this object. And I said, this is weird. I texted my grad student, Jake Hilton. I said, this is a true weirdo. That's what it says up here. This is a true weirdo. I have no idea what this thing is. The redshift that I was predicting was like 14 and a half, and I was like, but the thing is this object was big and bright and very confusing to me. And so I put it in my paper as visually rejected candidates. I said, I don't think this is not actually a distant candidate. There's a lot of things, like, for one, it's right next to another blue galaxy here. It's gotta be part of this. There's a lot, there's no way this is actually the distance. It's too big and bright. All the other ones look like tiny little red smudges. This is like 5 times brighter. No way, there's no way. But then, we looked at it enough, and we thought, may as well just observe it again as part of another thing and see what happens. And I was waiting, in January of this year, I was waiting to see what would it come back at? What weird thing was it? Because it couldn't be a distant galaxy. And when the spectrum came back, it turns out that it was actually at the distance we thought it was. This is the current new record holder, the farthest galaxy humans ever seen, JADE's GSE 14, at a redshift of 14.32. This galaxy blew me away. I was so stunned. I stood up from my desk, walked out into the hallway to find someone else, and I found grad student, or at the time, postdoc Fengwu Sun, who was just laughing because he saw the same thing I was and he just couldn't believe it either. None of us could. It was really an incredible thing. To show you a zoom in, this is like a fly through to that object to show you that it just happened to be right next to another thing that was kind of blocking it, like a jerk. As we zoom in here, you can see the actual images, and we're going to zoom in, and this right here is the galaxy that's significantly closer and just kind of blocking the way. It's photobombing the farthest galaxy humans have ever found. It's 5 times brighter than the previous record holder, and it's hundreds of parsecs. It's enormous compared with the tiny size of the previous record holder. This galaxy is a weird monster, really bright, very, very confusing. So as we go back, I have to ramp up the speed because there's a lot of nothing between the last one and this, and we finally get there. 285 million years after the Big Bang, this galaxy, we're seeing it. This is it, its spectrum, how bright it is compared with not only the previous record holder, but the paper that announced the discovery also had another object that I'd found that was also, this is the 3 farthest galaxies humans have ever found currently. University of Arizona, you should be very proud of the University of Arizona and our astronomers that work. You know, like, if our football team's going to get its butt kicked this weekend, we are not getting our butt kicked in the astronomy department. I will tell you that. This is Heisman Trophy 3 years in a row. It's an incredible thing. But, like, look at how much brighter it is and how much bigger. It's a crazy object. Even weirder, Jake Hilton found something pretty amazing, which is that JWST has a long wavelength instrument on it called MIRI that observes even farther than my beloved NIRCam, the one that took the original picture that we discovered it. And Jake comes up to me and he goes, you know it's brighter in MIRI. It's brighter in the long wavelength camera. MIRI, when it was designed, it's not as sensitive. No one thought that it would take pictures of galaxies probably beyond redshift of 8. And here it is, booming bright with the farthest galaxy humans have ever found. So Jake and I do the math and realize that what this possibly is indicating is that this galaxy has oxygen gas only 285 million years after the Big Bang. To make oxygen gas, a star has to live its entire life and die and explode. Imagine the characters in a 2-hour movie who live and die within the first 5 minutes so that the rest of the movie can happen. That's what's happening here. It's an incredible discovery, this object. And it caused quite a stir. Here's a bunch of headlines from around the world. My favorite, because I'm very vain, I apologize. When you're this close to your birthday, you can do things like this. Scientific American wrote an article, JWST detects the earliest, most distant galaxy in the known universe, and it's super weird. And they write in their first line, Kevin Hainline can time travel from his desk. Yes, it is true. Scientific American says I can, and I can. Now that time traveling is 1 second per second forward, but it's time travel. This is a thing that I think the astronomy community should be very proud of. This is a plot showing all the most distant galaxies that have been discovered and confirmed. This is far away and towards the Big Bang, and the next talk is this direction. That direction is towards where us now. GNZ 11, Hubble's farthest was this. This is how bright, if they're up here, they're bright. Every one of these dots represents a galaxy that had never been seen and was seen by JWST. All of these incredible distant galaxies are things that we've now confirmed, and we're learning so much about the early universe and how strange it is and how different it is than what we even thought it could be. It's really special. For instance, this just came out like 2 weeks ago, and I'm going to leave you with this. This is a galaxy that I showed on this one. It's called JADES GSC 131LA, and this is a galaxy, pretty faint galaxy, pretty good confirmation of it being a redshift 13, except it has this spike, and let me tell you, there is zero. I have shown this to a lot of astronomers, and each time they've told me, that's a mistake, something is broken. That's a mistake. Because the universe at this time, it's so early in the history of the universe is like a thick soup to ultraviolet light. And this is a booming lighthouse of ultraviolet light that somehow has found its way out of the thick soup to our eyes, and this has caused quite a stir among theorists. And that's my favorite thing to do as an astronomer, is annoy astronomy theorists. Your job is to figure out how that happened. I just got the picture, man. I don't know. This is yours, Woodstock's paper. So anyway, one thing that's really cool is even on your phone right now, you can go to this website and click on Viewer, and you can zoom around JADES and look at the galaxies. You can click this and put the SEDs where it'll put a circle down and find out the redshifts I predicted for all of them. It's a really incredible thing. This data is most of it's public. At the end of the year, almost all of it will be public, and astronomers have been using this around the world to understand the early universe. It's really exciting. So I'm going to thank you right there, and I think I have a couple minutes for questions, but thanks so much. There's no train, no choo-choo. So are there any questions? Can I answer any questions? Yes.
Hey Kevin, can you go back to the slide where you had like all the galaxies on that chart?
Yes, right here.
All those little gray dots, what are those?
Oh, these are my predicted ones. These are the ones that I have predicted. So you can see that we have some that look like they should be farther, but predictions are hard. There's other people here who are experts in that. There's quite a few people who are pretty good experts in that, and they'll tell you, especially if you put a couple beers in them, that most of these gray things probably not going to, especially when they're really faint. We have one that is actually off here. It's over at redshift 18 that we're going to try and go after in the next cycle if we get time. And man, if that's real, I don't know, I'll eat my hat. Please don't quote me on that. I do not want to actually eat my hat. Weirder things have happened. But all of the gray points are predicted objects. The ones that are colored, those we've been confirmed. So notice we confirmed the bright ones. It's harder to confirm the faint ones. Yes? Yeah, the galaxies probably are, most of them are just barely resolved, so they're probably clumpy star clumps. There's a very famous galaxy called Zwicky 18, and you should look it up if you can, because it's right in our backyard, and it probably is very similar to what these are in terms of its like big clump of stars being born. There's quite a few stars. Uh-oh. Is that the train coming, or are you getting it? That's a good way to kick me off. But they're not organized in disks yet. They're way too early for that. Big clumps of stars, GSZ140 is probably a little bit larger clump of stars, or a couple clumps that have come together, but nothing like what we have in the local universe. Galaxies are very pretty now. They were not at the time. They were messes. Any other questions? Yes.
Yes.
The problem is that unfortunately, there's a lot of uncertainty. We think it's some amount of oxygen gas, but it could be oxygen, it could be hydrogen, and the exact ratio we don't know. But the metallicity is not zero. There's some amount of metals, but we don't exactly know. We need to get a spectrum for it. So if anyone's on the tag, we're hoping to get a follow-up observation. But what we found for a lot of these is that they are not perfectly metal-free. They've got some evidence of stars living and dying in only a couple 100 million years, which is insane. Our sun is 5 billion years old, right? Like 200 million years for a star. They've got to be big old stars to have lived and died that early, which is exciting. Okay, is that it? Is that it? I'll stick around. You can ask questions afterwards. Thank you very much.
All right, thank you, Kevin. With that, we are going to break for intermission. We're going to take about 20 minutes for you to go refresh your drinks, go to the bathroom, whatever. So we will be back here right at 8:20. Don't forget to tip your bartender. For our Vestos Slifer expert, we have a prize for you over here. We also have our merch table. So if you want some more Spacecraft merch, come and get it during intermission. We'll see you back here.
Astronomy Club.
Oh, we also have a special treat for you tonight. The University of Arizona Astronomy Club is out near the railroad tracks, not on them, with some telescopes for you to look at some good to look at some of the stuff in the nighttime sky tonight. So go out, give them a visit during intermission as well. See you in 20. Welcome back, everybody. So, before we continue our journey through the very, very early universe, we come back to the present day, and we're going to have a little bit of news, the recent goings-on in astronomy. So, Danny, what is happening these days?
Thank you so much. Hello, welcome back for Astronomy in the News. Hey, there we go. Hello, I'm Danny Krolikowski. I'm a postdoc researcher at Steward Observatory. You might tell I am alone. My partner in crime, Dr. Jackie Champagne, is sadly busy. So I am sorry you will have perhaps a bit less funny of a news segment tonight, but oh well. It's been quite a while since we've updated you. I will not be updating you on everything. I briefly toyed with a summer news roundup set to Billy Joel's wonderful We Didn't Start the Fire, but that is something that Jackie could pull off, and I could not. So I will spare you. But to get started, I feel better doing things closer to home given the two talks being very, very far away. But to start off, astronomers, we always love the superlatives, right? The highest redshift, the smallest planet. I think Kevin did a wonderful job explaining why that matters to galaxies. Yes, there is some vanity, but these oddballs are what tell us the most about strange physics and how objects that we see hundreds, thousands, billions of light years away form and evolve. And that is not just true for galaxies, but that is certainly true for planets as well. Right? We have thousands of known exoplanets now. Most of them are what you might call typical. Typical not being typical to our solar system, but common. But there are some kind of oddballs out there that really perplex us. And one of these oddballs was recently discovered, the superlative, the most eccentric transiting exoplanet discovered to date by someone just across town at Noir Lab, Dr. Arvind Gupta, who gave a talk here not too long ago, actually, which you may have been here for. So what did he find? He found the planet TIC 241249530b. Add that to the phone book. And so what's interesting about this planet? So it's about the size of Jupiter. It was found with data from the TESS mission, which stares at stars to look for planets as they transit or cross in front of the star that they're orbiting. And then it was confirmed, and a mass was measured using data from the NEWIT spectrograph, which is at Kitt Peak, just a bit that way, that I actually work on every day. So that's pretty exciting. And so this planet is about the size and mass of Jupiter, which, okay, they exist. That's not super cool. But what's interesting is its orbit. So it has an extremely eccentric orbit, which means that its orbit is very, very like an elongated oval, right? I mean, the Earth orbits the sun quite circularly. We're more or less the same distance from the sun for the whole year. This planet, on the other hand, it spends a lot of time about the distance from its host star that the Earth is from the sun, but then, this is kind of washed out, it zips around really close to its host star, getting closer than about 10 times the distance from Mercury to the sun. So it gets really, really close to its host star, so it has this crazy orbit, and it's also orbiting backwards. What do I mean by backwards? How could there be a backwards? So, right, so stars rotate, so let's say a star is rotating counterclockwise, a normal planet might also orbit it in that same way, but this star is doing the opposite. So it has this very complex, highly dynamic orbit that that we know would often be unstable or temporary. So what does this tell us? Well, it means that this planet is probably in the middle of some evolution in its orbit. It won't be like this forever. And what we think will happen is that eventually, it getting really close to its host star, it will kind of trap itself there, circularize its orbit, and then settle in, orbiting circularly very, very close to its host star. And this is exactly how we think one pathway is for creating what are known as hot Jupiters, one of the first exoplanets types that we found of Jupiter-sized planets orbiting within just days around their host star, which astronomers were like, well, what? That can't happen. Well, it can, and it can form exactly like this. So this is exactly why these superlatives and these odd objects are so important to study. And this is really just the tip of the iceberg. It's a transiting planet. We can look at its atmosphere, and so we can really use it to uncover a lot more about how these strange planets can form. So our second story for tonight is even closer to home. It's a bit more of a future story, or a forecast, I would say. But I might not be able to make the next couple space drafts, and if you have been here watching me give news before, you might know that I refuse to pass up an opportunity to talk about icy moons in our outer solar system. So here we go, and this is a big one. NASA's next huge mission, the Europa Clipper, is getting ready, making its final preparations for launch to Jupiter just next month. So what is the Europa Clipper? It is a satellite that will orbit Jupiter and perform close flybys of its icy moon Europa, which, if you don't know, is a very, very cool object. It has a subsurface ocean of water and might have the ingredients necessary for life to form. So this is really a very important place to study in our solar system that we can actually get to learn potentially about how life forms, not just here on Earth, but a second genesis of life. So the Europa Clipper's launch window will open for a few weeks in October, on October 10th, and it is now starting its final kind of passes and tests and preparations for this launch. For example, they are doing tests on the solar panels. So the Europa Clipper, in this image, it has these huge solar panel wings that it uses to collect power. Totally unfurled, it'll be about the size of a basketball court. But they need to actually make sure that they'll, go. And so they're testing that now. It's actually so big they can only unfurl one at a time, so let's hope that's fine. But they'll make sure that once it's up after launch, these panels can deploy. And then also doing last preparations, mechanical adjustments for propellant to be loaded for when it launches into space. So if all goes well, it will launch next month and take the long 6-year travel to Jupiter, where it'll kind of sling itself around Earth and Mars, shoot off, and then insert into orbit around Jupiter in 2030. It will be orbiting Jupiter, but performing very close flybys of the moon Europa, and it has a very sophisticated suite of instrumentation where we will learn a lot that we don't. I mean, this is Europa. It's here. We've kind of flown by it before. We know a lot about it, but there's a lot we don't know as well. So it has cameras to take extremely detailed pictures of its surface. It has radar to probe into its interior. It has mass spectrometers, which will be able to taste its tenuous atmosphere and tell us what's in it. It'll look for its magnetic field. And all of that are very important components to understand how big its subsurface ocean is, what might be in it, and eventually could life be there. This really, it will tell us a lot and also serve as a pathfinder for a future Europa lander mission where we can actually go and maybe get up close and personal with Europa's ocean and look for that life. So this is one small step. It'll then be 6 years, so we have a bit of a wait to go. But I, for one, am pretty excited that even this step is being taken, and we're getting a little closer to finding those space undersea huge squids on Europa that I hope are there. They can stay there, but I certainly hope that they're there. Cool. Yeah, that's it. Just a quick update. Thanks, everyone. See you not next month, maybe soon.
All right, thank you, Danny. So our last talk tonight brings us to some of the earliest moments in our universe, and it will illuminate one of the processes that made the universe as we know it, cosmic inflation. Please give a very warm welcome to a fellow graduate student of mine at the University of Arizona, Joe Adamo.
Okay, can you hear me? Yes. Hello, yeah, I'm Joe Adamo. I'm a 4th year grad student. I'm in the part of the Arizona Cosmology Lab, so I do cosmology for a living, hopefully. Is this not, oh, is that better? Okay, and then before I start, I'm like 90% sure, certain my grandma's watching on the live stream, so hello. Thank you for watching. Yeah, give a round of applause. So yeah, the next 25 minutes or so, I'm going to be talking about the first billionth of a trillionth of a second after the Big Bang. So let's see if this works. So before we get started there, we have to actually talk about the Big Bang itself. This was actually kind of talked about already in the previous talk by Kevin. But so in 1929, Edwin Hubble, as well as many people before him, ended up discovering that galaxies were moving away from us, and the further away galaxies were, the faster they're moving from us. And this is him observing at the 100-inch telescope in California. I can't read the thing from here, but so this was a big deal at the time, and I'm going to go over the thought experiment that led to the Big Bang Theory here. So if you just imagine for a moment you're seeing galaxies from all around, and they're all moving away from us. So if that's true, then if you wind back the clock a little bit, they had to be closer together, or closer to us. So that's all fine and dandy, but if you wind back even further, keep going, eventually everything's going to be in the same point. So this seems sort of simple maybe nowadays, because this was like 100 years ago, but this was a big deal at the time. And over time this ended up culminating in what we now think of as the Big Bang Theory. Oh, that's not that Big Bang Theory. That came a lot later. This Big Bang Theory. So this was originally proposed by George Lemaitre in 1931, who I believe was a Catholic priest. But as well as many, I'm glossing over lots of the historical details here, but this was eventually heavily supported by Einstein's newish general theory of relativity. He actually famously had to hack his equations to keep an expanding universe from happening. So I mean, the basics of this theory is that the universe started out very hot, very dense, and over time expanded to the size it is today. And the Big Bang, of course, happened around 13.7 billion years ago, is what we believe today. And in the meantime, all of the stars and galaxies and stuff came about, and we get really cool pictures like you guys already saw today. So this is all great, and I'm sure most people have heard of the Big Bang Theory. Not the show, and maybe the theory even. But so there are actually some problems with this base picture that I'm going to talk about now. So the first of these is the flatness problem. So we have to talk about spatial curvature here. So if you apply Einstein's equations, which are extremely complicated, to the whole universe, you end up with three possibilities. So you can get what's called positive curvature, which in 2D is like a sphere. It would be like a 4D hypersphere in reality, which you can't visualize. You can have negative curvature, which is a hyperbolic type thing, which is even harder to visualize, or you can just have a flat universe. So those are the two big possibilities. And after some time, we've done tests, and we are pretty certain that the universe, and then the screen is warping a little bit, but I don't know if you guys can read. We're pretty sure the universe is flat. The screen is not flat, but the universe is flat. In order for this to happen, the amount of matter in the universe has to be equal to a specific value, which is down here. It's about a couple hydrogen atoms per cubic meter, which is very not dense, but that's average over the entire universe, so that includes all the galaxies and all the empty space. But so this is why is this? Okay, that's interesting. So this brings us sort of a problem, because if this, in order for the universe to be flat, the density of the universe has to be pretty much exactly the critical density here. And if it isn't, you'll end up getting, over time, it'll get further and further from that critical density, so the curvature will increase. So this is something that physicists like to call fine-tuning, which is where the space unicorn, the first of the space unicorns, come in. Because if you vary this parameter of your model a little bit, the outcome changes quite a bit, and lots of physicists are not comfortable with that. So that's the first problem. This is called the flatness problem. The next one is called the horizon problem. So if we look back in, like if you look in the sky basically in any direction, you'll see basically the same amount of stuff. This means that the universe is broadly homogeneous. So the problem that comes up with this is if you look all the way back to the earliest thing we can see, which is the cosmic microwave background, you end up seeing, like in this picture here, the universe is like much younger, right? And light has only had a certain amount of time to travel between things, or different points in space. In order for things to be like the same everywhere, the idea is that, like, you know, different points of space should have had to interact with each other, and there basically wasn't enough time for that to happen in the base Big Bang picture. So like this circle here is like the only region that like this point could interact with. Like it wouldn't have had time to like equilibrate with the other side of the sky. So the question then becomes, why is everything still the same no matter what direction we look? Is this more fine-tuning? So there's another space unicorn. That's the second one that makes people even more nervous. And then the final one is maybe a little more obscure. It's the magnetic monopole problem. So typically when you think of magnets, there's a North Pole and South Pole, like a bar magnet. And that is basically the only type of magnet you can have. You can't have like a North or South Pole on its own, except certain theories in particle physics called grand unified theories do predict that you should see magnetic monopoles, which particle physicists are very convinced that these theories should be true. So the question is, why haven't we found any magnetic monopoles? And so this is yet again the third space unicorn. We would really like to explain why we haven't found any of these yet. So these are the historic problems of the Big Bang model that inflation claims to fix. Inflation fixes all of these, and I'm going to go through the schematic of like the original idea for how this would work. This was all worked out in the 70s and 80s by a bunch of different people. So we're gonna get started here. So right at the beginning, and we're talking like extremely close to the very beginning, like 10 to the minus 36 seconds. The universe was very, very small and very, very dense. I think the size of the observable universe would have been like 10 to the minus 29 meters large. So, like, you know, you can't even picture it. But so, at this point in time, the universe was smaller than what we in the community call the particle horizon, which is basically how far light could have traveled in that in the time that the universe has been around. So if the universe is smaller than that, that means that, you know, a region on this side of the sphere could have interacted with the other side. So things could, you know, become the same temperature and all that stuff. So this is all well and good. Also, it's like insanely hot, 10 to the 27 degrees Kelvin. The thinking is, at this point, the universe starts expanding exponentially quickly, like increasing in size by a very large, like many, many orders of magnitude. And quickly actually getting larger than the particle horizon, which is also growing a little bit. And this is happening between 10 to the minus 36 and 10 to the minus 32 seconds is the thinking here. And it also cools off to only a balmy 10 to the 22 Kelvin. So that sounds like, you know, you got to get your winter coat on. So this truly insane degree of expansion happens and eventually stops at around 10 to the minus 32 seconds, where normal inflation or normal expansion takes over, and we get all the fun Big Bang, like all the particles start showing up. We get like Big Bang nucleosynthesis, which I'm not going to talk about. And then also there's something called reheating that people believe happens, which is that the temperature goes back up to what it was before. So this is the kind of schematic of inflation. So there's a trivia question here. So how much bigger do we think the universe got during this period? So we have 10 to the 12, which is 1 trillion times bigger. We have 10 to the 16, which is 100 million billion times bigger. We have 10 to the 26, which is I can I read that? A billion trillion times bigger, 100 billion trillion trillion, or 10 to the 36 times bigger, which is that like insane series. So what do people think? You just shout out if you got it.
Say A, 10 to the 12.
No, way too small. Yes. Z, 10 to the 26 times bigger than from before inflation. So if that is hard to visualize, which it is for me, if you are the size of a bacteria before inflation, after inflation, you are as big as the Milky Way galaxy. So that is crazy. I'm glad that, we've had a lot of money inflation the past few years. I'm very glad that it's not that bad. So yeah, this is like a really crazy amount of expansion that goes on. That's why it's called inflation, because it's just like inflating to a massive degree. So this solves all the problems I was talking about before. So the flatness problem, even if there was a density a little bit less or greater than the critical density, any curvature at the time would have been flattened out essentially. It's sort of like how you can't see the curvature of the Earth when you're standing on it because it's too big relative to you. So that would be the case here under inflation because it just got flattened out, so like to a very large degree. So that kind of fixes the problem of like if the density is a little bit different. Then we have the horizon problem, which I kind of hinted at already. So before inflation, the universe was small enough that things could have interacted and entered thermal equilibrium. So that makes sense why everything would be the same temperature and density no matter where we look. And then it also solves the magnetic monopole problem because theories suggest that magnetic monopoles would have been produced before inflation in high densities, which are then blown out of proportion by 10 to the 26 orders of magnitude, or 10 to the 26 times. So we would have very few, if any, in the entire observable universe. So this is some people would say copium for why we haven't found any of these particles, but this is an explanation for why we haven't found magnetic monopoles. And as a bonus, we actually also get an explanation for why there's structure in the universe. So there's something in quantum field theories called quantum fluctuations that happens in empty space, where energy changes rapidly in a small space. So these were happening before inflation. During inflation, these fluctuations are blown up to cosmic proportions, which end up as regions where it's just a little bit more dense or a little bit less dense. And then over time, this develops into all of the stars, planets, galaxies that we see today. This is just like a simulation for how that could happen. And this is a whole other realm of things people talk about. So what could cause this is a good question. That is maybe the first question that comes up when you think about this sort of theory. So originally people thought it could be the Higgs field, which I don't know if you've heard of the Higgs boson. Why don't you raise your hand? Yeah, okay. So this is a particle discovered in I think 2012 by the Large Hadron Collider, and the field that is associated with it is responsible for giving particles mass. And originally people thought that that would be what causes this, but that turns out that isn't possible. It was shown to be mathematically not feasible. So the current runner-up theory is a new field that has a value everywhere in space called the inflaton field. Very creative. And this would have a effect on the expansion rate of space, sort of like dark energy does, but it's not dark energy. This is different. But a higher energy in the field would mean that space expands exponentially. So like during inflation, it would be up here. And this is a schematic of something called slow roll inflation. So over time, the energy of the field would slowly roll down this hill into this little valley here. And this is when inflation would stop. And you get normal universe behavior. So this is sort of the standard picture of how the simplest way for how inflation can work, but there are also many wacky theories out there. So there's something called multi-field inflation, so you could have like multiple fields doing this and get really complicated diagrams, like I don't know how to read this. You can have eternal inflation. So I mentioned earlier that like there was a point where it started. Maybe it never, like it was always happening down to the very beginning of time. And you could even get regions where inflation didn't stop, and you can get like island universes separated by exponentially expanding space. You can have something called conformal cyclic cosmology, which is if you have a universe that is dominated by dark energy, it expands exponentially, and after an infinite amount of time, that like somehow magically becomes a new universe. So like it's like a cycle of constant universes, which I think is kind of cool. But there are more. There are many more of these, and it is a fun thing to like do if you're bored, to look up what people thought about for inflation theories. So this is widely accepted in cosmology that some form of inflation has happened, but it does have detractors, and you can kind of think of it. So we have these 3 unicorns on the side that motivated inflation, and then we have this even bigger one, which is what could have caused this thing we've come up with. And because we have not found any, as of yet, experimental evidence for inflation, like direct evidence. This is still a widely accepted theory, and people like myself are working on trying to actually find evidence for this. So I'm going to finish this up by talking about some of the ways we're trying to tackle this. So one of the big ones is something called CMB B-modes. So in most theories of inflation, once that period stops, you have a lot of gravitational waves that get generated, and those gravitational waves are unfortunately not strong enough to be detected by any feasible detector, but they could have an effect on the cosmic microwave background polarization. So like if you guys have ever had polarized versus unpolarized sunglasses, this is sort of the same idea, but with light from 300,000 years before the Big Bang. And it has a very, it's predicted to have a very unique effect on that polarization. And so one of the experiments attempting to fix this or like figure this out is the bicep array, which is the new generation of this. So stay tuned in the next few years. Maybe there'll be some interesting results here. And then the other one I want to talk about is something called primordial non-Gaussianity, and I could do a whole other talk on this because this is what I'm doing. So the idea is that certain more complicated theories of inflation predict that the distribution of matter is going to be different than like simpler models. So if you look at how matter is clustered at very early times, you see it's pretty much a normal distribution, like the hump and the normal distribution that shows up everywhere. Certain theories predict that to be a little bit off from the normal distribution, which we call non-Gaussianity, and we can parametrize that with this FNL. And you can see certain, if you can measure this and you can rule out certain theories, right? So one of the mission that is currently set out to try to figure this out is the SphereX NASA mission, which stands for something that is very long, complicated. It's a satellite that's going to launch in February. It's going to do an all-sky galaxy survey around, I believe, 300 million galaxies to try to measure this FNL thing. So stay tuned in the next 2 to 3 years, and this is what I'm working on as well, and we might have some results here. So that is my talk on the first fraction of a second before the Big Bang, so thank you all for listening. Who's got questions? What's my favorite inflation theory? Oh, I like the conformal cyclic cosmology. I think that's a really fun idea. I guess that might be my favorite, or the slow roll one, because the simplest theory is usually the most correct. I think having multiple fields to do something that one field can do is probably a little bit too complicated. But yeah, that's my thoughts. if there are no other questions, I'll be hang. Oh. So I think they will claim they have. Yeah. So the question is, has Bicep figured out how to handle cosmic dust? So for context, I think in 2012, the Bicep collaboration came out with results that they found these CMB modes to like 7 sigma, and so everyone was like, "Oh my God, this is amazing!" And it came out after several reanalyses and the Planck mission that this detection was due to cosmic dust. Like it could be fully explained by that. So it was actually a non-result. And I haven't read too much into this, but I believe they said they have learned lessons, and hopefully they are able to they're able to deal with that.
You didn't mention the creation of multiverses.
Yeah. So I mean, this which slide is this? So the eternal inflation kind of lets you have multiverse because you'll have island universes that you are inaccessible. This is a little different from like whether or not there's a multiverse that like in general. You can get that if you look at something called string theory, which is a huge can of worms. Also, certain interpretations of quantum mechanics will give you multiverses or multiple universes. But inflation, as it's a like standard cosmological paradigm, typically doesn't try to answer the question: are there other universes besides our own? Because like we can't answer that question. So.
All right, thank you so much, Joe. Spacecraft number 99. Let me pull out my notes to see when we're doing the next one. Yes, so our next show will be on October 15th. That will be Spacecraft number 100. So please come join us for that very special number. For our trivia winner here, please come join us and get your prize. Other than that, don't forget to tip your bartender, and thank you all for coming. We'll see you back here on October 15th, same time, same place.